Pouring a beer with a few or a lot of foam really annoyed her, and she determined to find out the secret of pouring a perfect glass of beer with the Six Sigma method she learned in the class. According to life experience and some related journal articles, the foam is one of the most important factors of beer drinking experience, second only to the taste. However, it's not so easy to control the foam when pouring out the beer. Also, it's ideal when the height of the foam reaches 1/3 of the overall height. In the measure stage, we use gauge R&R to identify and resolve measurement variation. The first step is collecting data. Our 3 operators used a ruler to measure the foam height of 3 cups of beer respectively. As the result of gauge R&R analysis showed, all components contribute variations less than 10%. For our chart, almost all of the points are within the control limits. And for X-bar chart, most of the points are outside of the control limits. So, we are able to conclude that the measurements of our operators are reliable. Here is a fishbone chart showing the analysis of the factors which may affect the height of foam. The most related factors were tested in the DOE process. They are the brand of the beer, the tilt angle of the glass, the pouring height, the temperature of the beer, and the time interval between opening and pouring the beer bottle. In the improved stage, we experimented on the DOE analysis with Minitab based on the results. During the experiment, we found that the angle and temperature of the bottle caused almost no impact on the result. So we narrowed our focus to the other 3 factors: beer brand, height, and time interval. In the new experiment, we tested 3 different beer brands: Qingdao, Budweiser, and Carlsberg. For each brand, we created a factorial design. We set the range of height from 0 to 7 centimeters and the range of time from 0 to 2 minutes. Then, we conducted the experiments based on the volume generated by Minitab for each group of tests and entered the data. From the diagram of residual plots for yield, we can find that the residuals are normally distributed with a mean of 0 and a constant variance. Therefore, there is insufficient reason to reject the model. And in the normal probability plot, red points indicate both height and time are all statistically significant, and the black point shows that the interaction of these 2 factors is not significant. In the response optimization plot, the red lines indicate the volume to hit our target, which also been used in the control phase. And the white area in the overlaid contour plot shows the volume range to produce acceptable results. In the control stage, we tested our findings in the improved stage and managed to control the pouring behavior perfectly every time. Our goal is to pour out the perfect foam with around 1/3 of the overall height. The limit height we said before is 2.6 centimeters, so the perfect foam height should be 1.3 centimeters. According to the result of the improved stage, we will likely to fetch the goal when we pour Qingdao beer immediately after opening up the bottle, while also setting the bottle at 1.4 centimeters above the glass. In the experiment, we set 10 subgroups with 3 pouring results in each group and measured the foam height 30 times in total. As the X-bar R chart showed, the volume of X-bar was 1.307, which was almost equal to our goal of 1.3 centimeters. Besides, all of the points are inside the range between the lower control limit and upper control limit. So, it concludes that the control method we conducted was effective and stable.